In the upcoming lessons, we're going to talk about how to make predictions using our model. And believe it or not, this gives us a chance to link together several concepts of the past lessons. In our technical section on gradient descent, we've talked extensively about cost functions and the role of the mean squared error cost function in machine learning. We've also covered how an algorithm that finds the best fit line minimizes this particular equation. And we've also talked a lot about metrics like R-squared, and we touched on how to compare different models. And finally, we've talked a lot about how to analyze the residuals. So how does this all tie together? Let's go back to the equation of the mean squared error for a little bit. Y hat in this equation is the value that is estimated by our model. Since we're using a multivariable regression with 11 features, our equation for y hat will actually break down into something like this. We have all the thetas and then all the features. Taking it a step further, we've also encountered the y minus y hat before. Y minus y hat were the residuals. The residuals are the actual values minus the fitted values. So what does that make the mean squared error? The mean squared error is just the residuals squared and then summed up and then divided by the number of observations, n. Now, do you see this squaring that's happening here? We're squaring the differences between the actual and the predicted values. We're squaring the residuals. And this is nice because we're treating the positive and the negative residuals equally, which means we can then add them up in the summation. But this mathematical operation of squaring the differences also has another effect. Think about this. What if the difference between the predicted value and the actual value was large? What if we have a large residual? What happens to the mean squared error? In this case, the squaring of a big number will increase the mean squared error massively, right? In other words, the mean squared error weighs the large differences more heavily, and thus it punishes large residuals. The effect of this is that it makes the mean squared error very sensitive to outliers. So that's one thing to be aware of. Now let's have a think about how the mean squared error compares to R-squared. And to do that, we're going to check out the differences between the two in Jupyter Notebook. In the past lessons, we've written some code where we plotted our residuals and calculated them and compared the residual plots of 3 different models. Now let's look at these models R-squared and their mean squared errors. In some of the previous lessons, the way we've worked with the mean squared error was by importing a function from scikit-learn. So we said from sklearn.metrics import mean underscore squared underscore error. And then we use this function to calculate the MSE. But in this case, we're using our stats model module here. And it actually makes accessing the mean squared error very, very easy because, again, we just have to use our results object to get hold of it. Here's how. Coming down here, I'm going to add a comment that reads mean squared error. And I can access the mean squared error from our results object by typing results.mse underscore resid. This will give us our mean squared error. And what I'll do is I'll store this in a variable. I'm going to call this variable reduced underscore log underscore MSE and set that equal to the rounded value of this whole thing. So I'll add a round function and have the results.mse underscore resid inside the parenthesis, put a comma after it, round it to 3 decimal places, and close it all off. And I'm going to do the same thing for the R-squared. So in our comment, I'll add R-squared, and then I'm going to copy this line, paste it down here, change the variable name to R-squared, and change the attribute as well. So results.R-squared rounded to 3 decimal places will be stored in this variable. Reduced underscore log underscore r squared is equal to round parenthesis results dot r squared comma 3 closing parenthesis. I'm going to take this here, these 3 lines of code and the comment, copy them, and I'm going to come down here to model number 2, the original model using normal prices and all features. And what I'll do here is I'm going to come down to the very bottom, paste it in, and change the variable names. The first one I'll call full underscore normal underscore MSE, and the second one I'm going to call full underscore normal underscore r squared. Now I'm going to hit Shift Enter on both of these cells since I've added new code. I think I didn't do it on the first one, but I'm going to do it on this one. Shift Enter, and then coming up here, I'm going to hit Shift Enter as well. This leaves us with our third model, the one where we omitted some variables and are still using log prices. And I'm going to paste in the 3 lines, the comment reading mean squared error and r squared, and then I'm going to change the variable names once again. I'm going to call this one omitted 1m double t omitted underscore var underscore MSE and omitted underscore var underscore r squared. And I'm going to hit Shift Enter. And now that we've added this code, calculated all these values, we can look at them side by side, which is what I wanted to do in the first place. So I'll put them in a data frame, pd.dataframe, parenthesis, curly brackets, single quotes, r squared, colon, and now I'm going to provide a list of all the r squared values. So the first one was reduced underscore log underscore r squared. The second one was full underscore normal underscore r squared. And the third one was omitted underscore var underscore r squared. Those are all the r squared values. Now I'm going to put a comma here after the square brackets, go down to the next line, and add our second key for our dictionary. It's going to be MSE, mean squared error, colon. And again, we're going to be putting in a list of values. So I can probably take this list here, copy it, paste it in, and then change that last thing here in the name to MSE. This is how I've named all my mean squared error variables. So that's easy enough. Let's take a look at what we've got. I'm going to hit Shift Enter, and what we see is 2 columns, one reading MSE and the other one reading r squared. Now the rows are still indexed by 0, 1, and 2, but we can change that by adding an additional argument here. So I'm going to put a comma up here, and then I'm going to supply the index argument. And I'm going to make this equal to, again, a list, so square brackets, and I'm going to put 3 values. The first one is going to be our reduced log model. The second one is going to be our full normal price model. And then the third one is going to be our omitted variable model. Refreshing our output, we see the names listed here very nicely. Okay, so let's interpret what we're looking at. First off, the r squared. We know that r squared is always between 0 and 1 for every single regression model out there. But what does this mean? R squared is a relative measure of fit. And r squared does not have any units, right? This means that the r squared doesn't scale with the data. It's always between 0 and 1. And in our table, we can see that the simplified model with the log prices has a higher fit than our full model with the normal prices, or of course, the model where we left out some variables. This one, in fact, has the lowest fit of them all. But what about the mean squared error? In contrast to R squared, the mean squared error actually is an absolute measure of fit. So not a relative measure, it's an absolute measure. And it has units, namely the units of the target, our y variable. That 19.9 that you see here for the full normal price model, the second one, is in the units of the target, which in this case is thousands of dollars. So this mean squared error here is actually approximately $20,000. Is this third one better than the second one because it has a lower mean squared error? And the answer is no, right? Because you can't compare the two because they're in different units. The model in the first row and the model in the third row are using log prices, right? Log prices in thousands. In other words, the scale of the MSE is different depending on the data that you're using. But of course, lower values of MSE indicate a better fit, and an MSE of 0 indicates a perfect fit. So you have to remember that when you're comparing models. Okay, so now that we've calculated our mean squared error, let's talk about how we would go about making a prediction for a house price. Now, I think that before we go ahead and do that, we should actually check out how the pros predict house prices. Two websites that are very good at this are Zoopla in the UK and Zillow in the US. But of course, you can go and hunt around on the internet to find a equivalent website that's a bit closer to home, depending on where you live. And you can either maybe pause the video and try out one of these websites to get an estimate for a home, or you can watch me go through the process. One word of warning though, Zillow thinks they're being very cute or clever in calling their estimate a zestimate. Yeah, so just something to note. So how did that go? Did you give it a shot? So yesterday, I actually tried using Zoopla to get a price estimate for Buckingham Palace or the Big Ben, but I didn't have much luck providing the postcodes for these landmarks. But funny enough, there were some properties listed in Windsor Castle, of all places, including the Windsor Castle Library. So yeah, I'm really not sure why. But I'll tell you what, I did dig around, and I want to show you how to get a property price estimate for this particular home. Let me show you the brochure. So this is an old brochure, and it's for this house in Kenwood. And as you can see, it's a very, very nice house. I think the agent, Knight Frank, was looking to sell it. And the story with this house is that it used to belong to John Lennon from the Beatles. That's right, this John Lennon. Contrary to popular belief, he did not live on Abbey Road, nor did he live in a yellow submarine. Okay, so let me show you how to get an estimate for his previous crib. Now, to get a valuation for this home on Zoopla, what I have to do is I have to go to Get Your Home Valued, and then I think it's come down here, and I think I have to click on What's My Home Worth? So I think the first place they send you is trying to get agent valuations. But I'm actually interested in the Zoopla estimate. So how much Zoopla thinks it's worth. So I'm going to click on this, get a Zoopla estimate. And then I'm going to punch in the postcode. So this was KT13 0JU. I looked this up. So John Lennon used to live on this postcode. And from that property brochure, we know that it's Kenwood, Wood Lane. So let's click on Get Estimate. Now we can supply some additional information about this property. The property type is it's a detached house. The property style is that it's a period home, and it's a freehold. I don't know how many floors it has, but I did check the brochure, and for bedrooms, it was 6 bedrooms, 6 bathrooms, and 6 receptions. I think it also had a big garden and a swimming pool, and for the internal area, according to the brochure, it's 1,110 square meters. So absolutely enormous. Now I can press continue, and then I'm going to tick swimming pool here, and I'm going to leave these other ones alone. I can't be bothered. But what's very interesting is that Zoopla knows how much this home sold for previously. This is actually public knowledge, right? If you're wondering where they're getting this from, they're getting it from the UK government's land registry. So the government basically tracks all the property transactions in the UK, and you can search for house prices of the previous transactions. And if I put in the postcode here, so KT130JU, and then say show results, then I can see here that for Kenwood, Wood Lane, in 2007, this home sold for £5.8 million. Yeah, so this is where Zoopla is getting its price data from. Yeah, they're getting it directly from the government. So that's one of the data sources. Now I'm going to confirm the information above is accurate, and I agree to the terms of use, and I'm going to say get estimate. And what we see is that Zoopla estimates John Lennon's former home to be worth £8.75 million. So it sold for 5.8 back in 2007, and today Zoopla reckons it's worth about 8.75. But here's the part I want to draw your attention to. I want to draw your attention to this value range that they're providing here. Because we don't just get a price, yeah? Zoopla isn't telling us, oh, it's worth 8.75 million on the nose. What we also get from them is a range around that price. We see that Zoopla thinks the property is worth between 8.16 and 9.34 million pounds. What Zoopla is actually telling us is that they are estimating this home to be worth 8.75 plus or minus 590,000 pounds. They're giving us an upper and a lower bound to their estimate. And this is a key component for making a good prediction. Why? Well, because it tells us how confident Zoopla is in their estimate. I mean, they're giving us this little bar here, confidence level high. But we can also infer how confident they are by how wide this range is. In other words, if Zoopla says, oh, it's 8.7 million plus or minus 600,000, that's very, very different from saying, oh, it's worth 8.7 million plus or minus 2 million, right? The point I'm trying to make is that when it comes to our predictions, yeah, so our forecasting that we're going to be doing, we're going to have to provide not just a house price, but we're also going to have to provide a range around that price. And believe it or not, this range actually has something to do with the residuals and the mean squared error. And that's what we're going to be looking at in the next lesson. But before you head over there, let me ask you a question. Have you ever used a website like Zoopla or Zillow to get an estimate for a property? And if so, please post the link of the service that you used in the comment section for this video. I'd actually be quite curious to know for which places on earth we can get estimates like this and for which ones we can't. At the time of recording, I tried finding the equivalent of Zoopla for Austria, but no dice. Yeah, the property market in Austria is just not as transparent as in the UK. And this property price transaction data that Zoopla is piggybacking off of to make their estimates, yeah, that they're getting from the land registry, is just not publicly available. Anyhow, I'll see you in the next video. Take care.